I think we can start. Welcome back, folks. For today's class, this is obviously the bigger part of the announcements we want to talk about, the upcoming exam one. Then after we discuss all those announcements, it's going to be kind of a choose your own adventure kind of a class. We'll do a student directed review. I'll take questions on any material you'd like to discuss, whether it be this document here. This is just the old lecture notes that's been converted into essentially worksheets for the purpose of studying those problems again. Or we could discuss any homework problems folks would like to take a look at. And I made a comment here that my exam is going to be highly based off your homework problems and this document here. So those would be probably the very first sources I'd take a look at to start studying for the exam. Probably the homework would be the best. I'd take a look at anything that seemed a little foggy there, anything that you might have lost points on. If you're not sure why you lost it or what the resolution is, definitely that's a good place to start. You can always email me for extra questions about that. Also for chapter 13, that one's kind of special. It's the odd one out. We did cover it. It's in there in the document, but it's also part of your homework problems as well. If you solve that early, I try to grade it early and send it back to you. And if you just about have it done and you do want to solve it early, I'll grade those within the work week on a first come, first basis. Just in case I run out of time, I might not be able to get all of them. But if you do want feedback on your work in chapter 13, try sending your work early and I will be able to provide that. Also, because chapter 13 is the last one there, I try not to add any kind of weird questions. It's going to be pretty straightforward based off what we did in the lecture notes on chapter 13 and what you're going to see in your homework problems as well. So not anything too wild on that one. That's my announcements at the moment. Any questions, folks, about our upcoming exam? Okay, it's not going to be a terribly long exam. And when it comes to these sections, it's pretty much like what you did in your homework, like we mentioned, except that seems weird with RStudio being so involved. But any component or any avenue where RStudio had to be used, it's already been included in the exam itself. Other things to keep in mind, let's get rid of this document here. Other things to keep in mind is definitely don't forget your calculator. We won't have a whole lot of calculator intensive problems on this exam, but it's good to get in the habit to bring this because it's going to be something we use on, say, exam 2, exam 3. So not too much on this one, but it's good to have it with you. It's going to be a closed notes exam, but you can use scratch paper and that kind of stuff. And this is the document that will be included on the actual real exam. So make sure you don't want to take notes on anything associated with this information or this information here. Definitely the central limit theorem will be part of the exam. And this is more just telling you what your statistics are, what they're trying to measure. The formula is not as pertinent on this exam. So that will be the formula sheet that's provided. And now we have a couple documents you might want to take a look at, like we mentioned. This one here, it's still a great one, but I've changed the design of this course a little bit, in particular on how the exam questions are asked. And so these are the older problems that were asked in different kinds of courses. They're still nice, but I had to strike through certain things that I wouldn't ask on our upcoming exam. So that's what the purpose is of all the strike throughs you might see on some of the problems. Might not be a whole lot of them, but there's definitely some here. We're not using the 6895 99.7 rule, for example. But if you do want the solution to this, I still have it in the very back. This is just my way of saying this is not on our current exam, mainly because of this being an older file. Well, that's where we're at so far, folks. Our assignment 4 is going to be due on Wednesday when we come on the day of the exam. And getting that done early again is doing two things at once. You are studying for the exam as you solve those problems. Well, any questions at all, folks, about those announcements? Okay, how about folks over in Zoom? Any questions at the moment? Okay, well, when we come back on Wednesday, February 7th, it'll be a weird class because, I mean, it won't be a class. Our class is split in two. Folks who come to the Idaho Falls class, the in-person section, we'll just have our exam here. And that's all we will be doing on Wednesday's class. It's not a terribly long exam, so if you finish early, you can still hang out and just be here if you like, or you can quietly leave it as well. For the folks in the section here, I sent instructions on contacting the Pocatello Testing Center for the online section, and that's just a matter of calling them up, finding a time that they can slot you in. If they can't fit you in on the day of the exam or the time of the them, it's okay to make different arrangements since it's understanding with that testing center. Sometimes it's, well, it does fill up and we just have to work around their constraints. So again, kind of weird. We're split into two different sections. It's really two classes running at once over technology. Any questions at all about where to go to take your exam or things like that? Okay, that's good to hear. If questions do come up, don't hesitate to contact me right away. We'll get it figured out. Aside from that, I guess this is the portion of the course where I'll turn it over to folks here. Any questions that you would like to go over for the purposes of review or take another look at or that kind of thing? How about folks on Zoom? Any questions that you would like to go over? They could be old problems from here, which are the new ones, or any kind of homework questions, that kind of stuff. Sorry, say again or again? Oh, there's a chat there. Missed that. Example 3 on practice problems. Okay, gotcha. Which set of practice problems were you wanting to take a look at, Zach? Was that on this document here or on the bottom document here? Version 1. Awesome. Let's take a look. And what I'll do, now that we're going into the review territory, I'm going to make a new file just called, once I find the document, there we go. Let's call this exam 1 review questions. And at the end of the day today, I'll have that, or probably tomorrow morning, I'll have that uploaded just right under here, exam 1 formula sheet. So let's take a look at example 3 on this version. Let's just steal it. That might work for us. Okay. So this one's a throwback from a while ago. It seems kind of weird looking at it without any context. It's not a brand new problem, but sometimes they feel like a brand new one. Got a chat first. Zach says, I have a crazy Wednesday class schedule with an exam of some sort. Yeah, that would be possible. Yeah, you could rearrange something specifically with that testing center. So anytime on Wednesday is going to be just fine to schedule the exam. Other questions about those kinds of things at the moment? Okay, well, taking a look at this problem, the first thing they're going to ask us is for each variable in the study, and that's already kind of nasty about this problem. We want to determine if it's categorical or quantitative. And if it's categorical, we have to indicate its categories. So in these data, we're looking at something to do with whether there's a relationship between weather conditions, so say the 4 different seasons, and the occurrence of violent crimes. So it looks like they're tracking homicides specifically. They have 1,361 of them, and they categorized it this way. So now we just want to know, what is this data we're looking at? What's its nature? What are the variable or variables associated with it? Anyone see what the variable or variables would be for these data here to start? We would have not quite the counts, but homicide is definitely a variable. This one's kind of tricky in a way. We'll come back to counts to say a little bit more what's going on with it, but it turns out this column is not a variable. It's not a quantitative variable neither, but this one is a variable. What would you call this, categorical or quantitative? Definitely, so we have, or sorry, not quantitative. This would be categorical because it's categorizing which season the homicide actually occurred in. So we'll say homicide is categorical, and its categories, you could write them out, winter, spring, summer, fall, or you can abbreviate it if it makes sense on the exam and just say the seasons. then that would satisfy that question there. Again, it's a little bit weird. That's the only variable. And so the wording here is kind of nasty in a way. It's almost like a trick question. But there's a problem with counts. It's not strictly a variable. All this is doing is showing the distribution of homicide, the actual categorical variable. And what we mean by that is it's just saying how many times its categories happen to come up. Winter came up 328 times, spring that many times, and so on. But it's on its own not a true variable. We have to be really careful when we get a table that looks like this. When it's one categorical variable summarized in this way, it makes it a little bit hard to determine what were the original variables of the study. But any questions, folks, with that write-up so far on Part B? It's kind of weird it starts with Part B. That's because Part A was to create the table, but that wouldn't have been a legitimate exam question. So it's been reformatted how you might see it as a real one. Then here it says, describe what you see in the display using the context. We have to be really careful with this kind of stuff. We can't say uniform for the shape of the data. Anyone see why that would be an incorrect description? And it's not necessarily because of that bump right there. Good call. The moment you have categorical data, we don't describe the shape of the data we see here any longer. And there's a good reason for that. The categories, well, there is an ordering to them for sure, but you could have started with summer and then went fall, winter, spring. It has a whole different shape if you went that way. Or maybe you ended with summer and then have the other seasons towards the left. Now you have a different shape of the data. So categorical data is weird in the sense that you can change the shape. Because of that, we'll say here, definitely if this is an exam question, do not, this is always weird to say, but definitely do not mention, let's emphasize that as much as we can, do not mention symmetry versus skew for categorical data. Only because that's not the kind of description we're going for. That's specifically for quantitative data. Quantitative data is a little bit different. There is a definite ordering, and you can't change what comes first. There's the ordering of the real line is specific. And so once you plot your data, it has a determined shape that you really can't change other than maybe changing the widths of the histogram bins. So instead of saying any of that, when it says describe what you see using the context, sorry, I didn't need to highlight all that. Really, I'm just looking for a really fast write-up. If I mention on the instructions, say 3 different things, then we have to do that. But here, it's really completely up to you. Any volunteers for what to say based off this distribution here, that bar plot? How about anyone over Zoom? Any one quick blurb you would say when you see this data? Keep missing those chats. Thanks for Hannah. The highest amounts of homicides happen in the summer. I'd say that's terrific here. And the thing that gives us really good credit is when it says using the context, we have to talk about definitely that this is all about homicides and the seasons they are occurring in. So we need to bring that into our description. So if this is all you said, let's say this is a real exam question and you said the highest amount of homicides, happen in summer, I'm now forced to give full credit for that because that's correct. You read the bar plot, you said what it's describing, and you knew not to describe it as quantitative data. I didn't give a benchmark for how much of a response to give, so that would qualify. That's important information since another thing to worry about on these kinds of exams is you don't want to get too wordy. It's not a long exam, but it's easy to get kind of sucked into one problem have a lot you want to say about it, but then spend 25 minutes describing the data that you see there. It's meant to be a kind of a faster problem where you move through these in a really fast or quick kind of manner. Well, we did, folks. That's pretty much a bona fide exam question. Any questions or comments running through this one? Okay. Any others that folks would like to take a look at? How about I pick one next? Does that sound all right to folks? Okay, probably one that might be good for us. I mean, if we're reviewing for an exam and this is our last section that's actually on the exam, how about we do one of those? That might make a lot of sense. So if we go to a chapter 13 problem, they're in here, they're in the homework. Let's see if we can get something that's brand new just to make it feel a little bit more fresh. So chapter 2, chapter 11, chapter 13. So let's take a look at, let's see, some stuff that's been struck through. This might be a good one. Let's take a look at maybe 18. And it might be helpful to say where we pulled these from. So let me put here. This one is from chapter 1. And this one's from chapter 13. Oh, sorry, looks like I also missed a chat. Hannah says, I still get tripped on the variables. Can we do another practice problem for that? Yeah, absolutely. So after this one, we'll look at variables next. Okay, I'll make sure to take a look at those right after. Okay, first let's take a look at what's going on in this problem. It says, in a certain population of fish, the lengths of an individual fish are approximately distributed as normal, with a mean of 54 millimeters, standard deviation of 4.5 millimeters, and we have a random sample of size 40 that's going to be drawn. We want to know what is the approximate sampling distribution of the sample mean. That's kind of a wild question when it just is thrown at you coming out to an exam. So we've been trying to give lots of hints about this one. The big one word that would give away what's going on in this problem is when they ask for sampling distribution. If you see that word right there, you're probably using the central limit theorem. So use the central limit theorem. The good news is that theorem is provided on the exam, so you could just look it up. Here, we'd probably start by saying X bar. You could write this out in words. A lot of people did this on their assignment, and I think that's terrific. So if you just say the sampling distribution of X bar is normal with these values, that's completely fine. If you're a fan of writing out with symbols, it would go about like this. Here's X bar. The tilde is saying is distributed as normally. We just need to know what goes into the very first position. Anyone see what value would be right here? Exactly, we grab the mean. Next, we grab the standard deviation, 4.5. And leaving it like this is a very common mistake. Anyone spot what the mistake is right here? Exactly. We're not actually using the central limit theorem unless, as you said, we involve the sample size. So over here, divide by the square root of n. So let's make that correction. It should be 4.5. Now take the division by square root sample size. They indicated it's a sample size 40, so I'll throw that in. And you don't have to numerically approximate this. In fact, in a lot of contexts, it's best just the way it is because you would type that number into RStudio as a homework problem and get more exact results without worrying about approximating it there. So it's okay to leave it just like that. So using the central limit theorem means don't forget about that part right there. So we've got it, folks. That's the sampling distribution. If it was a homework question, we'd probably calculate this probability right here using RStudio, but that's already been done for us. And really all we're going to do is interpret that probability. Interpretations involving the central limit theorem at the same time can be tricky. So my goal is to highlight everything that's a little bit tricky about this interpretation using that color pen. So let's begin. It's the same kind of interpretations that we're used to seeing. There's a lot of different styles for writing this out. You could begin here and mention the probability of, or you could say the percent chance of something. I'll go that route and say there is a 0.98% chance that, and this is where it gets tricky. So let's work it through and see how it goes. Any volunteers for what you would say very next? How about someone in Zoom? Anyone know what you would want to write out next at this stage? Oh, we got someone. Hannah says 0.98% chance that the length of the fish will be less than 52.34. That's really close, but it's still missing one little thing there. Anyone see what's missing on that statement that was written out? Thanks for contributing that, Hannah. Not so much the less than or equal to. You can convey a message that's strictly less than, or you could say less than or equal to, and you'd be giving the same correct interpretation. But it's more about that right there. Again, to me, this is the worst part of an interpretation involving the central limit theorem. Has to do with the mean itself. Exactly, Abby. So we have to make sure we say something about the fact that we averaged 40 different observations to come out to X bar less than that in this probability. So that's the part that's really easy to miss. And let's highlight it as we write it out. There's a 0.98% chance that, here we'll say either the average or the mean of, let's go with the mean of, it's more official language, but if you said the average of, completely fine. Might be better. That's more of an interpretation people are more likely to understand if they haven't taken statistics. But I'll go with there is a 0.98 chance that the mean of 40 observations, let me see if I can do slightly better than that. The mean of 40 observations, let's say the mean lengths of these 40 fish sampled. I wasn't terribly opposed to the last statement, but I feel like this one's better because we're bringing in the fact that the data is about the lengths of the fish and the number of fish right here. So I think it's better to just directly indicate that. We'll say here is less than 52.34. And I think this is in millimeters. And we did it, folks. That's pretty much how the central limit theorem questions are going to look like in this class. It's about understanding how to assemble the model. This is what you would do anyways before going into RStudio. And this is maybe the most important thing about the central limit theorem is, well, that's maybe not the best thing to say, but on the exam it is. The practical interpretation is very, very important for us as well. Any questions at all, folks, with the chapter 13 question here? Okay, let's take a look next. I forgot who asked that, sorry about that, but we're going to take a look at a variables type of question next. Then after we get through this one, think about which type of question you might want to go to after. We can just sort of load them in as we're going through this review. Aspen asks, for histograms that only end up with a few bars, say 4 to 5 bars, how should it go about determining the shape if it's not fairly dramatic? Oh, that's a great question. There's not really great rules of thumb for sure, but one thing that RStudio tries to do is whatever your data looks like, its own internal code inside RStudio for the histogram tries to tune the width of the histograms so it's telling you about where your data is concentrating and what a true shape would really look like. Essentially, RStudio is looking at your data. Suppose maybe your data is about like this. Very few bins in the actual histogram. RStudio is probably thinking that the best curve that fits your data is something that goes along like this. But if there's more drastic change, say around here, RStudio might decide there needs to be thinner binnings in your histogram to actually show a drastic change that might not be conveyed. So RStudio itself is trying to show the differences between what the shape of the data actually looks like based upon where it's really falling. I'm not sure if that completely helps, but another thing to take a look at is we have big problems with weird shapes also when the sample sizes are really small. So if you notice that the sample size is, say, not 40, but maybe 14 or even 8 or something like that, then we have to take the shape here with a massive grain of salt. And RStudio is probably going to use really wide bins in that case because there's not hardly any data. They have to range through all of the actual data from min to max. So when your sample size is small, we just try to do the best we can, and we're even more forgiving with symmetry versus skew. But the sample size is large, and you're getting rectangles in your bin that are pretty wide, just 4 to 5. RStudio is doing it automatic. That's probably what they're trying to convey something about the data, that maybe it's uniform, maybe there's not a lot of change, for example. But does that help out with that question so far, Denny? Awesome. I do want to come back to it. So let's say after we take a look at the variables, let's do another question that's more about symmetry versus skew to try to address that a little bit better. So let me put down here, we're going to go variables next. And then after that, sorry, one moment, struggling with all my cursors here. One thing that Microsoft Word is not very good at is white space. There we go. If you don't remember to put extra white space down here, you can get kind of trapped. So let's just put a bunch in. Okay, so let's take a look at variables. And next we'll take a look at symmetry versus skew. Okay, before we get too far in variables, I did want to come back to something we mentioned right here, but this is actually pretty tricky. If this was a question about variables, that alone is a tricky question. And the reason for that is, for these particular data right here, this is not how the study was actually collected, how the information was collected. The actual original data probably looked like this. Season, or rather not season, it might have been homicide. I'll just say homicide number. That was probably some kind of code. They might have been pulling it from like crime databases, maybe the FBI database. So there's some code, like a student code that would go there. Let's just call this maybe homicide number 1, as morbid as that sounds, number 2, and so on. Here you would have season. And it might go winter. If they're pulling a random sample, there's no reason to assume all the seasons are in order. Next one could be summer. And it keeps on going down in the set. We had one problem like this in the homework where this was tricky right here. This is not a variable that counts. That's just showing the distribution of the variable. This is also not a variable. That's an identifier. That's just saying what's the difference between each of these homicides. We have to give them an identifying code, a name of some kind. So this one's not a variable. Let's actually indicate both of that because it's really very tricky. So this one right here, not a variable, and neither is that one. The actual variable is season. It's categorical because the outputs, the responses are non-numeric. They're just how we're categorizing each one of the homicides. And so this is definitely the categorical variable. Any questions about that so far, folks? Okay, again, it's really tricky. And if you're given a table like that, always imagine if I collected that data, those 1,400 were how many observations, how would I have formatted it? It probably would look like this, and maybe an Excel sheet, some database, anything along those lines. It wouldn't have started out this way necessarily. But let's return to maybe a larger question about variables. Let's see, do we have anything here along those lines? That's pretty much like a problem we just did variables wise, so that's probably not a good one. Let's maybe go to this one right here. This is, again, I indicated probably the better set for the sake of reviewing for upcoming exam one. We did do this one in class, but maybe this is a good one to come back to. Okay, let me know if this was kind of on the lines of the question you were thinking about with the variables as well. Now, based off everything we see in the screen, this question can be pretty tricky for identifying variables. If you're looking over here and thinking, not a variable because it's an identifier, not the case on this one. The identifier is suppressed. It might have been the name of the child, something along those lines, but it's not here at all. Column 1 is not an identifier. It's a true variable in this case. If we look throughout the columns, we have quantitative, quantitative, and quantitative for the first three. And then the last two were the categorical variables of the study, which again is confusing because they look numeric, but they were coding these up for 0 for one sex, 1 for the other. 0, I believe, is non-smoking, and the ones, there are ones in there, was for the children that did smoke. So these were all considered categorical. Well, any questions about considering these different variables so far, folks? Okay, well, let's take a look at next. Dealing with symmetry versus skew. These kinds of questions, again, are always very tricky. So let's see if we can draw out a couple situations, maybe some random scenarios. Let's make this a bona fide class activity. We'll decide on our own, do we have something that's symmetric, or do we have something that's skewed? So I'll put on the left a histogram. On the right, we'll just put in what our determination is. And fastest way to make a histogram is just to make our student do all the work. So let's make it work for us. Kind of nice that it remembers the last state it was in, but it can be annoying sometimes. But let's take a look. The way I'll generate the histograms is by going sample gets R for random, norm, so we'll pull from the normal distribution. Well, let's make the shapes wonky by taking a sample size of 10 and just see what happens. So this will have a mean of 0, standard deviation of 1. If we just end the inputs right there, we'll do a histogram right away. And we'll kind of cherry pick these, try to figure the best ones to make a discussion. That one's a little bit weird. You know what? That one should be just fine. Let's take this one as our very first one. So we have a weird sample. This did come from a normal distribution. Well, our best hardware implemented normal distribution with pseudo-random numbers and all that fun stuff. But for that very first one, try to get that window here. Observing that the sample size was just 10, what would you all say in this situation? Is this at least roughly symmetric, or would you say there's a skew to the left? Any volunteers for the direction to go on this one? Yeah, there is definitely a little bit of a skew to the left. I would still say that's probably, it's got some interesting gaps. The main peak is here. I would probably accept that as an answer for this as a real exam question. And that's kind of the uncomfortable nature of these kind of problems. I think Aspen is mentioning here. There is no cut and dry rule for this. You can do formulas about the skewness or kurtosis of your data, but those aren't used very often and they have limited value for inferential statistics. We just have to make a lot of judgment calls. Here, for a sample size of just 10, we might say that there is a slight left skew. I think this will be more helpful if we put here shape. That's what we're answering, the shape of the data. And the distribution is given by the histograms we'll have on the left. So I'd say there's left skew to these data. There's nothing I would consider to be major with outliers. I wouldn't say there's any influential outliers, although this one leaves the main peak of the data, and it hasn't done it by very far. If it was pulled over to this location, we might have called it an outlier instead. So that's one down. We have something that is a slight left skew. If you said at least roughly symmetric on this exam, I probably would accept that one as well, because this one becomes borderline. But I'm really just looking at the response you give on the exam question, the data you're looking at. If it looks plausible based on what we're both seeing, you wouldn't lose points on this. Let's see if we can make one a little bit more dramatic, where it's definitely going to be one answer or the other. That could be a little bit fun. So let's do the same thing over here. And here's our next one, about the same as before. Now, this one, if I saw this on an exam, I'm really expecting one answer. This one is a lot less cut and dry. And I do try to write my exam questions so that it feels less debatable. Most people would say, oh, it's definitely this or that. So here's our second example of the same thing. Well, what would you all say on this one for the shape of the data? Symmetric or skewed? I would definitely agree with that. We have skewed data. Which direction would you all say it's skewed to? Is this one going left or going right in the skew? Absolutely. It's trailing off here, meaning skewed to the right. So skewed to the right. You might also say positively skewed or right skewed, anything along those lines. You have to mention the non-symmetry, so skewed, versus as well as the direction rather. So say which direction it's going in as well. So I feel like this one is a lot less cut and dry. If this was the distribution on an exam setting, I'd say we would have to say skewed for credit on this one here. Any questions so far, folks, on either of those graphs? Okay, let's try maybe one last one. I mean, the table's here, so we might as well. Here's our last run of it, and this time we're going to make a change. Let's say we pull from the random sample of size 30. 30 seems weird. Not really trying to go with the essential limit theorem rule of thumb, but let's just do 30 because it's a nice number. So at size 30, pulling from the normal distribution and getting that shape would be kind of weird, but it could happen. People might see this and think there might be a new effect that we didn't think about. There's data pooling right here, but also right here, these might be considered bimodal data. But for true bimodal data, you would probably want a bigger separation right in the middle. I'd probably still say we're looking at roughly symmetric data. Actually, I would say it's highly symmetric at this point. The things that taking away from symmetry, like in this example up here, aren't as major on this one at below. So let's see if we can get something even more symmetric. Geez, for sample size 30, that's kind of weird shapes. lots of weird shapes. Trying to cherry pick one at this point. But this is the nature of pulling random data. Symmetry is not as common as we would like to see, unless you're bumping the sample size up a lot. At sample size 300, you're probably going to see this more and more often. In fact, let's see if that really happens. Let's go for sample size 300. We get a shape that looks like textbook normal distribution at that point, which it should. It did come from a normal distribution. So at sample size, this was bumped all the way up to 300. We would just say here, highly symmetric. Even if there was one additional piece of data going here, we would probably still say highly symmetric. And we expect deviations from perfect symmetry for sure with real data. Well, any questions at all, folks, about considering shapes of histograms at the moment? Okay, while we're on this page then, this is definitely an exam question, and it was a homework question. It was in the notes as well. We often like to decide what statistics we would use based off the shape of the data. And for these data, if you said it had a slight left skew, you're probably going to use M for the median to represent the center, and the interquartile range to represent the spread. Likewise, same idea over here. This is even more so. In this case, we would definitely want to use M for center and interquartile range for the spread. But once we convert to highly symmetric data, or at least roughly symmetric, this is the case where we're going to start using X bar to represent the center, and S to represent the spread. Any questions about that so far, folks? Okay, and just to clarify one more time on this very top one, viewing it as an exam question, I would give this full credit right here. There is a slight left skew. Because you're thinking skew, this is an appropriate thought to have. We use these for skew data, so this would be full credit. But I would say if this was real data, if this is your capstone master's thesis project or anything along those lines, for sample size of 10, this is actually not too bad. This would be symmetric enough to actually use the sample mean X bar and the standard deviation S. We wouldn't be in that much trouble until the skew gets a little bit worse out here. Well, that's dealing with symmetry and skew and those kinds of matters. Let's see. Only things we haven't hit on is normal distribution, but we kind of talked about it with the central limit theorem. So at this point, I'll leave it up to the class. Which direction would you like to go next? Were there other topics that folks would like to delve into? Find about 30 seconds is always a good amount of time for everyone to consider their options, that kind of thing, especially if you're typing up a response on Zoom. Oh, we got a response. Example 5, chapter 2. Thanks, Zach. Let's take a look. So example 5 on chapter 2. Were you thinking this problem right here? Awesome. Let's take this one right here. I think we can just get one whole screenshot on it. Okay, so lots going on this one. Let's see. It says recruitment, addition of new members to a fish population, important measure of the health of ecosystem. Oh, I think I remember we did this one. This is data on the rock salt in the Bering Sea on these years, and there's a year missing inside there. This time we have it displayed in a box plot. We want to comment what we see using the context of these data. And this one, as an exam question, is asking for very specific items. So When it says comment to what you see on the display, we're really thinking right here, the box plot specifically is where we're going to do all of our commenting. And so for credit, we have to be talking about that plot itself. So let's write out our response up here just for space consideration. So if we're going for three things, this would probably be the bigger thing I'd mention. What would you say about that, Dot? What would your response be for that one? Exactly, we're looking at an outlier. We have an outlier of, it's way out here, so 4,700 million. If you like, you could look up the data and find the year it happened, but that's not really what you have to do. If you'd like to do it, that's not a bad thing to do either. I'll solve the problem following the instructions to the letter, strictly looking at the box plot. So we have an outlier of about 4,700 fish recruited. That was a really good year, and because this is an important fish, that's kind of a shame it didn't come back. But that's something that happened with the population as it evolved. We have one item down, and we still need to come up with one other thing. Oh, before I forget that, let me take a screenshot here, Zach. The next example, awesome. I'll put it right here just as a reminder. Okay, so how about for folks on Zoom next? What would be your second thing you'd want to mention when you're looking at this box plot? I think that's a great idea. Zach mentions the fact that the data is skewed towards the right is true on this. So right skew means we have data that's trailing off in this direction as opposed to this direction. So if we're looking at the whisker portion of the box plot, definitely looks like skew and the outlier supports it. If we're looking at the inner portion within the box, we're only looking at the central 50% of the actual observations. But within that central 50%, there's a tiny distance here. That's 25% of the data. This is another 25% of the data, more spread out on the upper end. Looking at the scale, it's increasing as you go up. And so that's definitely a right skew. So we can say these recruitment values, once I figure out how to spell recruitment correctly, give me a moment. Recruitment, I even have a cheat sheet right here. These recruitment values are skewed to the upper end, or right skewed might have been the easier way to say that as well. So that's definitely a great thing to mention. Thanks for mentioning that. There's a whole bunch of things you could say. As long as you've got 3 items down, you're in good shape. And for our next response, most of the data is between about 500 and 1800. Absolutely. I like that part because that's one of the main features of the box plot, telling you what the interquartile range essentially is, and the fact that central 50% of observations are inside there. So that's a really great response, I'd say. Let's say here, about 15%, 50% of all observations, try to write a little bit small to fit this in, are between 500 and 1800. I'll put here the word approximately. You wouldn't necessarily have to say approximately though, because it's understood if you're reading from the plot, you are visually approximating to do that. Well, those would be great responses. There are 3 different ones. When it says mention the context, there just have to be context somewhere so that I know that you know we're thinking about the original context of the problem. So if you've said fish somewhere, if you said recruitment value somewhere, then I'm happy. On this last statement, I didn't even mention the context. I just said 50% of observations. But I wouldn't take off points for that. As long as you mention context somewhere, you're all set. Any other questions, folks, or comments with part A? Okay, well, now that we mentioned this statement right here, good call, Zachary. Mentioning skew right here, skew to the right, helps us with part C now. We want to know what statistic best represents the center and which statistic best represents the spread. That was weird. That shouldn't have been plural. That should have been singular as well, but we'll move past that. This problem is kind of unusual and it's a little disconcerting on an actual exam. It's not asking you to calculate the statistic. It's just saying, which one would you choose if you were about to calculate it? So here for the start, we can say for center, use M. And when it says spread, let me say this a little bit better. Use M to measure the center or for the center. And use IQR, interquartile range. That's just the distance from here to here. For the spread. So that solves our part C down there. Any questions, folks, so far? Okay, and let me take a look at the reminder. Next example after that one. So that would be this one right here. Good call. We haven't done a normal distribution problem yet. Our second problem was the central limit theorem question. This one might be a good one to take in stages. So we'll bounce back and start with this one. So it looks like we're dealing with another fish population. Most statistics look kind of familiar. I'm not sure, or parameters really. I'm not sure if they're exactly the same from their central limit theorem question. So it tells us we have a mean length of 54 millimeters and a standard deviation of 45 millimeters. So I'm starting to write out some exam questions that look a little bit more like this these days. You'll notice it in the homework, the lecture notes, that we're usually going to see information formatted in this way. And we just have to know when it says mean length, we're referring to mu as 54 millimeters. And standard deviation is referring to sigma as 4.5 millimeters. Now compare this to the central limit theorem question we did. If it asks for the probability distribution, let's see, what do we know about this? Well, they told us it follows a normal distribution. So probability distribution of X could be done as fast as this. X, which is the length of a randomly selected fish from the population, is distributed as normally with mean of 54 millimeters going in first and standard deviation of 4.5 going in second. So that takes care of our part A there. That we are definitely an adventure for the next ones. I think this is a good one to take a look at. I'm glad you mentioned it. Next thing we're going to do is sketch the graph of the density curve for this distribution. And homework, we had options. We could use technology, but here we just have to know what that sketch looks like. It doesn't have to be pretty when you go to sketch it out, but it does have to have certain features. Let's mention it as we go to plot this. First thing I want to do is plot this incorrectly. So this is not a good one to copy in your notes unless you're mentioning this is not quite right. If you draw a normal distribution that goes like this, I'm not worried about the shape here, but this is the problem. Your curve can never hit the x-axis, let alone delve below it. So we have to make sure our curve is always above the axis. This is another one we should definitely avoid. The curve has no sharp points, so the normal curve cannot do something like this, for an example. That would be kind of weird. That'd be a cusp in the problem. And I don't think I'm this picky, but it's also good to not draw a normal curve that goes like this. Although I don't think I'd be too picky. This would just be weird because the curve never comes up again. Once it leaves the center, it's always being damped on both sides, the far left and the far right. So as long as your curve doesn't have any of those features, you're in great shape. If it looks terrible, then that's okay. So this one is not that bad. I was trying to draw a horrible one. And if you want to draw it pretty decently, going a little bit faster as opposed to drawing it slowly and considering each step, that's when they come out weird, I think. Just let your hand kind of do it, then usually they're not too bad. So either one of those is completely fine for full credit. Let's settle on that one. So there's our curve. Next question it asks us to do is, well, they have a statement. Actually, I think we can pull the rest of the problem in at this point. Oh, and we ran out of white space. Let's get some more. Okay, so this is our next question. It says the probability that a randomly selected fish from this population has a length less than 50 millimeters is that. So it's pre-calculated for us. We don't have to do it ourselves. It gives us the practical interpretation as well. There's a 18.7% chance of selecting a fish less than 50 millimeters from that population. The whole problem is asking us to shade the portion of the graph that corresponds to that probability. So it's a tricky question because you can't just drop 50 anywhere. What you would probably want to do is start by placing the center that orients us. 54 goes here. Next, consider the standard deviation. It's at 4.5. So if we go about 4.5 to the left, we're right around 50. So 50 should be somewhere in this region. It doesn't have to be perfectly plotted, but it can't be way out here. That's way too far for the graph. We know it's almost 20% of the area. So shading about the right amount of area is meant to be kind of a guide for us as well. So it ought to be somewhere right around here-ish. And then shading doesn't have to be fancy, just draw some lines or scribble around here, and then that's for full credit. So this probability is represented by this area now. Any questions about that so far? Okay. Then the last concept questions, we saw one of these in the homework set for chapter 11, is really the fact that we're dealing with areas. We know that the area of a vertical line segment is exactly 0. And so that's the issue here. You could say just briefly, areas are probabilities and the area of a line x equals 50 is 0. I'd say that's a good way to convey this. There's other things you can say. Some people discuss the fundamental theorem of calculus. If you're integrating on exactly one point without an interval, you're just going to get 0 each and every time. And that is what RStudio is trying to do. It's trying to integrate this curve, finding that area right here. Same issue on this one. We wrote out an explanation, but it pretty much goes like this. RStudio cannot differentiate between a solid line here. Solid line is when it's less than or equals, versus a dashed line right here. That's when you have less than. The reason there's no way we can differentiate between the two is the area of the line is exactly 0 itself. So it makes no difference if you go less than 50 or less than or equals to 50. You can't even specify that in RStudio if we try. The probabilities are always the same. But a quick response to this might be for part E. Since probability x equals 50 is 0, probability x less than 50 should be the exact same as probability x is less than or equal to 50. We gave a more long-winded explanation when we did this in the course notes, but for an exam setting, I think that's a fine enough explanation to get right to the heart of it, give the full explanation, and move on to the next problem. But any questions at all, folks, with this here? Okay. Well, it looks like we kind of ran through the gamut of things we're going to see. It'll be pretty much this kind of stuff that we did in class. And more importantly, I'd say the most important review document is going to be what you were doing in the assignments. So take another look at assignments 1, 2, and 3, and 4. If you still, yes, and 4, if you feel great about those, then you're doing great. take a look at as well as this document here. If you can solve those problems cold, I know they're old problems we solved before, but if you can still solve them cold, you're doing great. And this one, just be careful with that document. Some problems won't be asked. Some problems might be asked in a different style, but for the sake of additional problems, I'll do this for the other exams as well. Well, any questions that folks would like to get into next for the review? Any one thing that folks feel like we maybe just didn't hit on or anything along those lines? I feel like this question here was a really good one, by the way. I'm glad we did this one for the review. Okay, well, what we're going to do next is, well, what we planned to do next was go over to chapter 14, start doing some inferential statistics. I feel like getting into a chapter 14 problem, and we could, but getting into a chapter 14 problem in 14 minutes might not be the most productive thing for us. I think we'll learn this material better if we come back to it after the exam. So I'm in class a little bit early today. I think that we spent some great time on these review questions. If you do have additional questions, I'll be just here, happy to help out. So have a great night, folks. If you have questions, feel free to hang around. I'll be happy to help until 6:45. Otherwise, I'll see you all on Wednesday. Thanks, folks. And thanks for the contributions and things like that. I think it's student-directed review day is kind of hard, but we'll make it work.